So just as we weren't willing to use the definition of the derivative to compute derivatives forever, we'd also like to come up with ways to simplify the computation of integrals. So there's 5 results here that are fairly commonly used. I'm going to prove 2 of them. The other 3, I will state them, but I will not prove them. The first one, you are familiar with it from calculus, is integration by parts. Let f and g be 2 integrable functions on the interval AB. With antiderivatives, capital F, capital G. Obviously, capital F refers to the antiderivative of F, and capital G refers to the antiderivative of G. Then, the integral capital F, little g, between A and B is what we typically write as fx times gx between A and B, which we mean to be, we evaluate the function at B and then we subtract from that the value of the function at A minus the interval between A and B, little fx, big gx. How do we prove this? Let's look at the product. Capital F with capital G. Now F and G are both differentiable on account of the antiderivatives of little f and little g. So H prime exists, and according to the product rule, it will be f prime gx plus fx g prime x. Now we know what big F prime and big G prime are. This is fx, little fx gx plus big fx, little gx. Well, we also know that the integral of h prime is going to be h at b minus h at a. That's from the fundamental theorem of calculus. Which version? Look it up. Now we know what h prime is. H prime is this thing. So the integral of h prime is in fact this integral here. And h at b minus h at a, by construction, this would be fb gb minus fa ba. And you can rearrange the terms. We'll try to keep little g, big F, what we had here. Solve for this by sending this to the other side. It's proven that the integration by parts formula is in fact valid. Here's another result which is quite useful. This is the first substitution theorem. Let's assume you have some interval j, alpha, beta, and some function phi from j into R, which has a continuous derivative on j. One thing that we must have in order for this to be true is that phi itself is continuous, even though it is not explicitly stated. If f is continuous on an interval I, so this is AB, which contains the image of j by phi, then the integral between alpha and beta of the function f phi at t times phi prime at t dt is going to be the integral from phi alpha phi beta of the function f at x with respect to x. Now we've assumed here that f is continuous on the interval ab, so it is R integrable on AB and on subsets of AB. So we can define the integral between phi at alpha, which is somewhere in AB here, I should remind you of that, x. Let that function be big F at x. And I told you here that if f was R integrable on AB, it meant that it was R integrable on subsets of AB. I'm really talking about subintervals here. Now, by the fundamental theorem of calculus, second version, f is going to be continuous. That's true no matter what, as soon as f is R integrable, and it is going to be differentiable here specifically because little f is continuous, with f prime at x equal to little f x. This is true for every x in the interval AB. What follows is set h at t to be f phi at t. T is some point in the interval j on which phi is defined. H is the composition of two continuous functions, right? F is continuous by the fundamental theorem of calculus second version. Phi is continuous because by assumption phi prime was continuous. The derivative of phi is continuous. That can only happen if phi is continuous. So here this is the composition of two continuous functions. We have that h is continuous on the interval j. Furthermore, we know how to compute the derivative of h. We use the chain rule. Now this function here is going to be equal to little f at phi at t times phi prime at t. Little f is continuous by assumption, phi is continuous by assumption. This composition here has to be continuous, composition of continuous functions, and by assumption, this is continuous. So this product is continuous on the interval j. So the derivative of h is continuous. It's going to be integrable as well over the interval j because f composed with phi is continuous, thus integrable. Phi prime is integrable because its integral is phi. The product is itself integrable. So not only is it continuous, this function is also R integrable. So we use now the fundamental theorem of calculus first version, and if we integrate this function h prime at t between alpha and beta, it will be the same as integrating f phi at t times phi prime at t between alpha and beta. And because we know that the interval of h prime is h beta minus h alpha, the fundamental theorem, and that this is equal to f phi beta minus f phi alpha. So this expression, again by the first fundamental theorem of calculus, will be the integral between phi at alpha, phi at beta of the derivative of this function, which is exactly little f. There are three more results I'm going to state about Riemann integration, but I will not be proving them. Theorem 63, second substitution theorem. So we let j, as before, be some interval alpha beta, phi some function of j into r, again with a continuous derivative on the interval j. Let's assume that phi prime at t is never equal to 0 on the interval j. Let I be the interval AB, phi at j contained in I. Let psi be a function from I to R, which is in fact the inverse of phi. That such an inverse exists is guaranteed by the fact that the derivative of this function phi, which is continuous, is never 0. So the function is always monotone increasing or monotone decreasing, and so the inverse exists. It's just the reflection, if you want, when we invert x and y. If f is continuous on I, then we have the integral between alpha and beta f phi at t is the same as the integral over phi alpha phi beta of f at x times psi prime at x with respect to x. Possibly not quite the way you had seen that in calculus. Now, I'm not giving you an example of integration by part. I'm not giving you an example of integration by substitution or for these other theorems here, because this is something that you do know from calculus. Okay? But you need to be sure that you know how to integrate by parts and how to integrate by substitution. I'm not providing you with a proof of this result, although it is not that complicated to prove. I will also state a mean value theorem for integrals. So we have a function f, which is continuous. It's continuous on the interval ab, which is closed. It is bounded on ab. Let p be some function from ab to r, which is r integrable with p at x always greater than 0. Then you'll be able to find some point c in the interior of the interval ab, such that the integral of the product f at x times p at x is equal to f at c times the integral of the function p. Recognize here the same sort of structure as we had for the mean value theorem differentiation. These aren't the same thing. It has the same structure. Can you come up with a geometrical interpretation of this state? What would it look like? And finally, a squeeze theorem for integrals. Let's say you have some interval ab, 3 functions from ab to the set of real numbers, all bounded. Is it sufficient to be bounded to have Riemann integrability? If they're all bounded and f and h are Riemann integrable, and f at x is smaller than g at x, which is smaller than h at x, for every x in the interval ab, and if the integral of f over ab is the same as the integral of h over ab, then you can conclude that all 3 integrals take on the same value, in particular that g is integrable.